Well, good morning. It's 8:32, 2 minutes late getting started for differential equations. The trouble is I'm the only one in the room now. I was sort of waiting to see if someone else was going to show up. And I think someone probably will, but they're not here now. So I'll wait and do announcements until at least one more body is in the room besides me. And because there are a couple of fairly not super significant, but things you might need to know coming up. So I would normally ask if there are any questions on anything we've covered so far, but nobody's in the room to ask, so let's just pick up and go from there. We're in Chapter 4, Higher Order Differential Equations, 4.2, Reduction of Order. And we did the first example on page 132 last time, and we're ready for the second example now. Here is how example 2, this is on page 133, goes. The function y1, let me get my pen set up, y1 is equal to x squared. Okay? They tell you that is a solution of this differential equation. X squared y double prime minus 3x y prime plus 4y equals 0. Okay? Now, they tell you this is a solution for that differential equation. Now, obviously, this differential equation is a second order differential equation. So therefore, it needs to have at least two independent solutions. So this, even though it is a solution, it is not your general solution. So that's what we're asked to find the general solution of the differential equation on the intervals 0 to infinity. Okay, now that kind of suggests to me anyway, it's probably going to be a log involved. Okay, could be a 1 over square root of x, possibly, but my guess, or it could be just anything over x, but my gut feeling is a log will be involved. First, let's make sure this is a solution. Let's do y1 prime, and that's 2x. And y1 double prime is 2. Let's see if this works then. This says that x squared times 2, that's y1 double prime, minus 3xy prime. Okay? So you got a minus 3 and a 2, so that would be a minus 6 x squared, because your y prime is 2x. Okay? Plus 4 times x squared. The question is that equal to 0. Okay? Well, let's see. 2 plus 4 is 6, minus 6 is 0. Yes, indeed, that is a solution. Okay? Now, we didn't have to do that, but I always like to do it to make sure I don't waste my time trying to solve a problem that is misstated. So that is indeed a solution to that differential equation. It works, okay? Notice there's no arbitrary constants in it, but we can add those later, okay? But what we're asked to do now is find the general solution of that differential equation on the interval 0 to infinity, all positive real numbers, okay? Now, one of the first things we want to do is get it in standard form. Now remember, we identified standard form last time by, and it's very similar to what standard form was for a linear first order differential equation. Let's get the coefficient of your leading derivative, you might say, your maximum derivative, the second derivative here, to be 1. So that means we're going to have to divide by x squared. Divide this by x squared. and divide this by x squared. Okay? Now we see one reason that x can't be 0, okay, is that we're dividing by x squared. But of course we knew that couldn't be 0 either because that was your coefficient of your y double prime, and that can never be 0. So therefore you're either going to have to be x is less than 0 or x is greater than 0. They chose to have us do these on the positive side. So we do that, these go away, and you wind up with y double prime minus 3 over x, because this x cancels one of those, times y prime, plus 4 over x squared y, and that's equal to 0. Okay, so that's our standard form. All right. Now, if you go back up and look at the general case just above here, it says that our y2 should be y1 of x on the times the integral of e to the minus the integral of p of x dx divided by, this is inside the bigger integral, y1 squared of x, okay, dx. All right. Now, once you get it in standard form, this is odd. So let's identify things. What is your p of x? This right here. P of x is equal to minus 3 over x. Okay? That's the coefficient function of your y prime. Okay? With the sign attached. And that would be minus 3. So the first thing we do is do this inner integral here. And this is going to be the integral of, and it's minus the integral of minus, so that makes it a positive, 3 times dx over x. Okay? And of course this is going to be 3 times the log of x. I say 3, and for some reason the pen writes 2. Okay? I don't know what's going on here. The old gray cells are not connected well. Okay, 3 log x. That's your integral there. We raise that to the e power. So before we do that, let's write this as log of x cubed, and then raise that to the e power, and e to the log x cubed is just simply x cubed, because e undoes the log undoes the e. Okay? So what do we have now? Our y2 is equal to our y1, which is x squared, times the integral of, and your numerator here was x cubed, and your denominator is x1 squared. x1 was x squared, square that and you get x to the 4th, and then you have your dx. Okay, so what is this? It's x squared times the integral of 1 over x dx, right? Well, that's going to be x squared times the log of x. Okay. Now, at some point here, we need to put our plus c in there, okay? But don't sweat that now. We'll just leave it right like that with the understanding, once we give the general solution, there's going to be our c's. So our general solution is y is equal to c1 x squared. Notice we didn't have a constant up here either, plus c2 x squared log x. There's your general solution. Okay. Now, I hope you fiddled around with linearity enough now to realize these two functions are linearly independent of each other, x squared and x squared log x. There's no way you can combine them in any way to get 0 unless both C1 and C2 are 0. So there's your general solution, okay? So I think that's all we have to do here. And now we see indeed that the x has to be. All right, here's Charles. Good morning. All right, let me get set up with my projector and stuff. And I already got the lights the way I wanted them. We'll hold on just a minute until the projection comes on. All right, while we're waiting for that to come on, let me go over the announcements. I decided not to make them until I had at least one warm body other than my own in here to hear the announcements. First, student course evaluations, anytime, right?
Yes, sir, I'll take care of it.
Okay. You have up until August the 8th, but I'm not going to be here on August the 8th to remind you. So,
I'll do it then.
All right, good deal. Thanks. Okay. And let's see, that's the first. The second concerns my office hours. And as soon as I think I have them figured out, they change again. Not that my schedule's changing, but other demands on my time. So normally, on a Tuesday, like today, as soon as class is over at 10:45, I would have office hours from 10:45 up until around, I put on my thing 4:30, but I found if I leave at 4:30, I barely make it over to Birmingham East Campus in time to start class on time. So now I'm trying to leave by 4:15, okay? But not today. Today we have a big hearing that it's a planning hearing, reviewing what we did for last year and beginning the process of what we're going to change or adjust or whatever for next year. And that our hearing starts at 1:30. So that means I've got to leave this campus before 1 o'clock to get over there by 1:30. So there's no way it's going to be 4:25 or 4:15. It's going to be at least, no later than 1 o'clock. Okay?
Please, I have the answers number 4 right there. Everything else is just.
It's on the paper.
Yes, sir. I have that right there.
Yeah.
I have the statement. And they're all numbered. And I'm
Right.
highlighting this time, so we don't have to work as hard.
Okay. All right. Good deal.
I'm sorry to interrupt. Go ahead. Sorry.
Okay. Now, I was here pretty late last night trying to get most of the things together. One thing didn't print properly, so when I came in this morning, I printed that. I still got copies to make, so I'll be doing that after 10:45. And for those that go in our planning notebook, I've got to do hole punch for all those. So I will be here for a while after 10:45, but as soon as I get the copies made, the holes punched, and the documents in the right order in the book, then I'm heading to the Birmingham West Campus. So I don't know what time that'll be. It'll be sometime between, I'll be leaving here sometime between 11 and 1, okay? Getting there sometime between 11:30 and 1:30. Just depends on how rapidly I can get the stuff done, maybe if I can get some help doing it, all that kind of stuff. So that sort of bums out office hours today, almost completely. I will be here right after 10:45, but not for very long, okay, because I've got all that other stuff to do. But I'll be over on the Birmingham West Campus at 1:30 for our hearing. It probably won't go past 2:30. And then I'll probably head over, if I have any changes to make, which I probably will, I'll get those done, and then probably head over to the Birmingham East Campus and get ready for that class that's later in the day. But I'll go over there and be grading papers like crazy. Okay. So that's how the rest of the day. I will have office hours, but they're not going to be on this campus. They'll be over on the Birmingham West or East campus. I have a few this morning, but not that many. All right. Thursday, now Mondays and Wednesdays have been pretty much the same. 8 to 8:30 and 5:30 to 6, okay? It's Tuesday and Thursday's been messed up, okay? Well, Thursday, now that the planning hearing's out of the way, hopefully I get back to normal on Thursday. Should be 10:45 until about 4:15, okay? Normal office hours, though they haven't been normal lately. But then I got an email. I saw it yesterday, but didn't get a chance to read it until this morning. They've called a meeting for next Wednesday, okay? That's supposed to be final exam week. You know, I'm supposed to be administering a final. I think I can get someone to cover it, but it's over on the Birmingham West Campus, and I think it's about 1 o'clock. So I'll have to be leaving here probably no later than 12:30, and I'll go over there, and the odds are I will stay over there the rest of the day, okay? I don't know. The meetings, it's typically a long meeting. I'm guessing about 2 hours, so something like 1 to 3. By that time, for me to drive back here, there goes another half hour wasted, so I'll probably just stay over there, grade papers, get things caught up on Blackboard, that kind of stuff, and probably won't come back next Wednesday until Thursday morning. And at that time, I guess people will have been leaving things under my door and stuff like this. I'll be grading like crazy all day Thursday. Okay, now, which kind of leads, what is it like for next week, or the rest of the term? We have class today, we have class Thursday, we have class Tuesday. Then I'll give you your final exam on, which is just the last test, on Tuesday. And I may even give it to you Thursday if I can get it run off and stuff like that. And you have until Thursday to get it turned in. Yeah, she said, here's, no.
First, Thursday,
Okay.
the first, because Wednesday is the 31st, so we have until that first, submitted to the last test.
Okay, so that on the
Last test, we do it the first.
Okay.
August 1st.
Yeah. Next Tuesday, last day of class is the 30th. Then I'll either give you your exam this Thursday if I can get it run off and stuff like that, so you can start working over the weekend. And then we'll have class on Tuesday, and then you need to get it into me by Thursday. Tuesday, Wednesday, or Thursday, I'll take it any day. Okay? The reason I say that, technically that's when it's due, but we have to have grades in by noon on the following Monday. So I don't want to have a lot of grading to do Monday morning because I've got to get all the grades in by then. Now, in addition to that, and on top of that, we're really needing to leave town. I'd like to take Monday off, so I'd like to get all the grades in by late Thursday. And so therefore, please get it in by Thursday. If not, I'll have to give an incomplete, and then as soon as I get back and I pick it up, grade it, I'll change the incomplete to whatever your grade is. Okay.
Because I won't be able to make it Thursday. You do a mental test. That's not common.
Okay, I couldn't tell.
No,
I heard you couldn't make it Thursday.
Yeah, because that's going to influence my time as far as I have to complete it.
Yeah, what?
That's going to influence my time.
Right.
I will have to complete it. Just right. Meet the deadline.
Okay.
If it's Thursday. Are you on this campus Thursday? You're going to campus Thursday?
Are we on this campus?
Yeah, I guess so. You have class.
Yeah. Okay. Okay, you mean this Thursday or next Thursday?
This Thursday.
This Thursday. I'll be here for this class. I'll be here up until 4:15, at least as far as I know. Then I'll be leaving to go to the Birmingham East Campus where I have a class this Thursday. Same thing for next Tuesday. I'll be here for this class, be here until 4:15, then go over there for my class over there. Then the following Thursday, a week from this coming Thursday, that's the day that they're due in, I'll be here, same thing. We won't have class though, but I'll be here from 8 o'clock in the morning until 4:15, 4:15, maybe 4:30, I'll head over to the Birmingham East Campus, and there I'll be there until at least 6:30, probably closer to 7. Okay, but I'll be there until I get everything done. So those are the options. You can get things to me. Like I said, I'll try to get you your final exam. If I can, I'll try to get it run off by Thursday so you can have it over the weekend. And then anytime next week you can turn it in. We will have class Tuesday, so we will be covering material that may be on the final, so I wouldn't want to turn it in until after I've been to class or at least heard the class or whatever. So, but then get it into me anytime later Tuesday, Wednesday, or Thursday, whenever you can get it to me. Like I said, anytime up until Thursday afternoon at 4:15 or 4:30, I'll be here on this campus. But at that time, I go over there. If you can't get it over there, slide it under my door here, and when I get back from the break, I'll get it graded and the incomplete change to the grade. So, okay. So we'll shoot at it. Is this close to your last course, isn't it?
No, sir. I need linear algebra.
Oh, you do?
Yes,
okay.
sir. I've already.
Yeah, but this isn't a prerequisite for it, so you'll still be able to register.
Okay, yeah, no, that's my next question. I think Math 126 is the prerequisite for linear.
Second?
Is Calculus 2 the prerequisite for linear algebra?
Yeah, I think so. Okay. And you've already had that, right?
Yes, sir.
Yeah.
Yes, sir.
Yeah, linear algebra is 237. This is actually a course beyond 237. So, yeah, so you'll have no trouble registering, even if you took an incomplete in this class. I don't know if you will. If you did, it won't bother your registration. All right, good deal. Yes?
I got a question. What time does your Cal 3 class start on Wednesdays?
What time? What
time is Cal 3 on Mondays and Wednesdays?
It goes from 2:30 until 5:25.
Okay. We're done with chemistry. I took my final yesterday, so
yeah.
I can come to class tomorrow.
Tomorrow? Okay, and Monday?
And Wednesday.
Yeah, well, Wednesday there's no class, you just turn in your final.
Yeah. So I can come to 2 days.
2 days, yes, it'll be so exciting. Okay, yeah, excellent. Okay, all right, good deal. Any other questions, housekeeping, in the term type questions? And have you done the student course evaluations? That was the first thing. Please do those before the 8th. Okay. Well before the 8th. Okay. Now, before anyone got here, I had done example 2, the bottom of page 133. We're in chapter 4, higher order differential equations. 4.2 is reduction of order, and we were on page 133 and 4.2, and this was example 2. Okay? And what we based it on was the formula we came up with last time. Okay, and just a reminder, what they gave us was one solution for this differential equation. Okay? That's a linear second order differential equation. Okay? Defined on this interval, 0 to infinity. And one reason 0 is not included is if x were 0, then your leading coefficient would be 0, and this would be a second order differential equation. In fact, neither term would be, both terms would be 0. And then you have 4y is equal to 0, and obviously y would have to be 0. So that's not a very interesting problem. So you can't include 0 on the domain. So they chose to use positive, and as soon as I saw that, I thought there's going to be a log in your future here, okay? Because they chose only positive. They could have done it just because of the x squared there and just chosen to do positive rather than negative. But first thing we did then is get it in standard form for a linear equation, which means divide by that leading coefficient equation, or coefficient expression, okay, in x, function in x. So we divided everything by x squared, including the 0. I didn't show that, but we did. And this became y double prime minus 3 over x times y prime plus 4 over x squared times y equals 0. Okay. So this is in standard form. Now we identify our p of x. Now, back when we did linear first order differential equations, the p of x was the y prime was by itself, and the p of x was the coefficient function of your y. Now, the y double prime is isolated, and the p of x is the coefficient function of your y prime, which is minus 3 over x in this case. What do we do to it? It's very similar to what we did to it in the linear first order case. We integrated, okay? But here it's the negative integral of that. And a negative integral of a negative, that negative times negative will be positive. Pull the 3 on the outside, and you have the integral of dx over x, which is simply log x, okay? 3 times log x. Well, because I know the next step we're going to do is raise that to the e, so I don't want the 3 in there. Let's move the 3 up here by our rules for logarithms that we know and love, and make that log of x squared. Then raise that to the e power, just like it shows here, and that gives us x cubed. There is your, this integral, this numerator right here, x cubed. Now, the formula here that we derived or went through last time, the y2 is your y1 times the integral of this thing we just did over y1 squared dx. So here's the integral up here we did first, now we're doing the integral here. Okay? Well, your y1 was x squared. The integral of, this came out being our x cubed. y1 squared, x squared squared is x to the 4th, dx. Well, that gives you an x squared. The integral of x cubed over x 4th is another 1 over x dx. Okay? And again, that integral there is a log x. So it's x squared log x. Okay. Now, notice in neither integral here have we done a plus c. Okay? Even though they're indefinite integrals. One of the kind of reasons you can think of doing that, we're just coming up with the functions. Okay? y1 we were given, y2 we just got, x squared log x. Now put our arbitrary constants in front of those. What I pointed out before any of you came in, these are linearly independent solutions. And any linear combination of those forms our general solution. So this is the general solution for that differential equation, given that that was the first solution. All right. Any questions on that? Y is equal to C1 x squared plus C2 x squared log x. And that finished 4.2. They have the remarks at the top of page 134 that can eat up so much time. I don't see anything particularly egregious here, so they don't have anything in bold print or anything else. So basically we finished with 4.2. And then the same homework exercises I gave you before still apply. Any of the odds 1 through 15 that are in the back of the book, please try to do some of those. Any either 17 or 19, if they're in the back, try to do at least one of those, and number 21 if it's in the back. Now, the discussion questions, there's only 3 of them. I doubt if those have answers in the back. If they do, you can look at those as well. So let's move on to 4.3. Okay? Now, any questions for our array system? Okay. 4.3 is homogeneous or homogeneous linear equations with constant coefficients. Okay? Finally, for the first time in chapter 4, we will actually be solving some differential equations. Not given one solution, find the other solution, or verify this solution, or do this. We'll actually start solving some. So we'll do homogeneous linear equations with constant coefficients. What do we mean by homogeneous or homogeneous in this context? Yes, whatever you have on the left-hand side is equal to 0 on the right-hand side. Your differential equation is equal to 0. Okay. Now, it says as a means of motivating the discussion in this section, as if they haven't put it off so long, let's return to first order differential equation, more specifically to homogeneous or homogeneous equation, AY prime plus BY is equal to 0. First order linear differential equation. Okay. We know that A cannot equal 0. If it did, that means basically B has to be 0. That's not very interesting, okay? So A can't be 0. But A can be any other constant and B any other constant. Okay, that type of equation can be solved either by separation of variables or with the aid of an integrating factor. But there's another solution method, one that only uses algebra, okay? Now, let's make an observation. If we solve this, okay, that equation, let's solve it for the y prime, sort of like we did before. Let's divide both sides by a. Since it's not 0, that's okay. Okay, so now we have y prime plus, now I'm going to write it now, b over a times y is equal to 0. Or another way of looking at that is y prime is equal to sum k times y. Okay, if you subtract the b over ay from both sides of the equation, b over a, b is a constant, a is a constant, a is not 0, that's just a constant, so we can just change it and make it k. So y prime is equal to sum k times y.
So b over a equals k, shouldn't it be negative?
Okay, negative b over a equals k. Yeah. I left off that step just because, okay, but you subtract b over a times y from both sides, and you get y prime is equal to minus b over a times y, and now we make this equal k. Okay, it's just a constant. Can be a positive constant, negative constant. It's not, a can't be 0, so it is defined everywhere. Could even be 0, but that wouldn't be very interesting. But there's a differential equation. Now, can you think of any function that when you take its derivative, it would be just a multiple of itself? What function would do that? Every time. What's my favorite function in the world to integrate the differential?
Oh,
E, exactly. Okay, so let's just make a guess that y has to be some e to the, let's just go on and call it kx. Am I being, no. I think they want to call it mx. Okay, so let's do that.
Is this like the same mx, like y equals fx plus b?
What's that?
Does this mx like have anything to do with like a slope or anything?
Not really, not in this context. Good thought, but no. Okay, it's just some number. Well, let's see. If that's true, what we would do next is do y prime would then be what?
Y prime equals
M e to the mx, right? And then you've got it. Okay.
Wouldn't y, so y double prime would be x squared?
Yeah, you don't have a y double prime. Yeah, but yeah, it would be. Hang on to that thought. We'll be coming to that. So this says m e to the mx is equal to k e to the mx. Okay? Well, guess what? That means m has to equal k. All right? Because the two sides are exactly the same. We can do that because e to the mx is never negative, never 0. Well, it could be negative, I guess. No, I don't think it could. So you can divide by it, and that would be perfectly fine. Okay? So if we substitute that, y prime is that. Now let's go back into the a's and the b's, okay? I don't know why they're running in circles here, but they are. Let's go back to our first equation here. This one, ay prime plus by equals 0. Homogeneous, okay? So now we have a, and the y prime was m, e to the mx plus b times y, which is e to the mx, is equal to 0. Okay. Similar to what we had before, but now they put it back in the a's and b's. Don't mess with the k's anymore. Okay? Because e to the mx is never 0. Ever 0. You can divide both sides by everything on both sides by e to the mx. Well, okay. Hold off a minute. I'm going to do it the way the book did. I like to do it this way, but they don't. Okay. Let's first factor out the e to the mx. That'd be e to the mx times am, that's morning, plus b is equal to 0. Okay. And this makes more sense, I guess. You know that e to the mx is never 0. It's always positive. Always positive. No matter what the m is. Never 0. So we can divide that away, and that gives us am plus b is equal to 0. So m is equal to minus b over a, which is exactly what we said before. Okay? Now, all right. I'm going to erase this mess. They just sort of run around in circles and you think, okay, we got the point. Let's get to something. Here's actually a differential equation. 2y prime plus 5y is equal to 0. Okay? Now, it's not necessary to go through the differentiation and substitution of e to the mx into the differential equation. We merely have to form the equation because we know e to the mx is going to do, and when you take the derivative of that, you get an m, so you wind up with what they call an auxiliary equation that's 2m plus 5 equal 0. If you can do it if you want to, let y equal e to the mx. And then take the first derivative, plug it in, you're always going to get this equation. Okay? 2 times m plus 5 equals 0. Okay? Now, from that we can see, subtract 5 from both sides, and you get 2m is equal to minus 5, so divide by 2, and you get m is equal to minus 5 halves. Plug that back in here, y is equal to e to the minus 5 halves x. Okay? There is a solution, and you put a C1 in front of it, and that's your only solution. I mean, that's your general solution. And that's good from minus infinity to infinity. There's no limit on what your x can be. E is good everywhere. Okay? Now, so in this section, we'll see the foregoing procedures produce exponential solutions for homogeneous, linear, higher order differential equations. They don't have to be second order or first order, any order, as long as you have, look at the title of this section, constant coefficients. So now the general form is a sub n. No longer a sub n of x, not a function of x, the constant a sub n times the nth derivative of y plus a sub n minus 1 times the n minus first derivative of y plus a sub n minus 2 times the n minus second derivative of y plus dot 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 plus, they get all the way down to, I'm going to do a sub 3 y triple prime, is that right? Yeah, plus a sub 2 y double prime plus a sub 1 y prime plus a sub 0 times y equals 0. Okay? There's your generic linear ordinary differential equation with constant coefficients. Okay? And anytime you have something like this, your assumption is y is equal to e to the mx will work. But you don't even have to do it. You can just plug it in and you'll get it. These coefficients are real constants. They can be positive, negative, fraction, decimal, rational, irrational, anything. It's just that a sub n cannot equal 0. Any of the others could be 0 or not. A sub n can't be 0. Okay? Now let's back off again to this one. A y double prime, this is second order, plus b y prime, they're no longer calling a sub n's, they're a, b, and c, plus cy is equal to 0. A linear second order ordinary differential equation with constant coefficients. A, b, and c are constants, and a is not equal to 0. B and c could be 0, but a, b, and c are any other real numbers in the world. A can't be 0, but the rest of them can, or any other number. Okay? Now, again, our assumption is y is equal to e to the mx. There's our assumption. Okay? Now, if you go in and do the y prime is equal to what? Help me. Me to the mx, right? And y double prime is? M squared. And e to the mx. So if you put these in here, you get a m squared e to the mx plus b m e to the mx plus c e to the mx equals 0. Right? Okay? And again, you can factor out or divide away the e to the mx, and what you have left is am squared plus bm plus c equals 0. And guess what that is? That's a quadratic equation in the variable m. Okay? How do you find the zeros of that? One of two methods. Anyone know? How would you find the zeros of that?
You would do the quadratic formula
or factor. Exactly. Let's do the two things. Factor it if you can. If you do, you get two values for m. Unless one of them, you get only one value and it is a repeated value. That could happen. Or you could get no solutions. But if you use a quadratic formula, it could be that you get two irrational solutions. That's okay. Those are real numbers. But you could also get two complex solutions. That's okay. We're going to learn how to handle no matter what you get. One solution, two solutions, no real solutions, fractional solutions, irrational solutions, or imaginary solutions. We're going to deal with all of them. And they will all give you this. Now, this equation right here.
M is your variable, though, correct?
Say again?
M is your variable though, correct?
Yes, m's a variable here. We're finding the value for m, which will make that equation true. Whether it's a real value, a complex value, repeated value, whatever, we're going to deal with that m. Okay? Now, what this equation is called, they're going to get around to it sometime. Yeah, there it is on the top of page 136. This is called the auxiliary equation for this differential equation. That's the auxiliary equation of the differential equation. Okay? Now, let's go straight to the quadratic formula. Okay? Even though you might be able to factor the thing without knowing A, B, and C, you can't factor it. So let's do the, how that happens. The quadratic formula. Okay? How would that go? M is equal to, anyone remember how the quadratic formula goes?
Oh, negative B.
Minus B plus or minus
The square root
of
B squared minus
B squared minus 4AC, all divided by 2A. Perfect, perfect, perfect. Okay? Now, that gives you two possible roots. One is m equal minus b plus the square root of b squared minus 4ac over 2a, and the other is m equal minus b minus the square root of b squared minus 4ac over 2a. Now, there are three possibilities here. Okay? One possibility is that both of these m's, okay, let's start with the, remember back when you did quadratic formula, probably for your first or second time ever, they called this the discriminant, right? And there were several possibilities here. One possibility is that discriminant could be 0. In other words, b squared is equal to 4ac. If that's the case, you only have one solution, minus b over 2a. Okay? Now, you need two, so we're going to get back to that in a bit. Okay? But that's one possibility. The next possibility is that b squared minus 4ac is a positive number. That's going to give you two real solutions. Now, if that positive number happens to be a perfect square, then you have two rational solutions. Okay? And that's really nice. That meant you could have factored the thing anyway. Okay? But it could be those are going to be irrational. As long as it's irrational but positive, you're okay. Okay? You'll get two real irrational solutions or two real rational solutions. The third possibility is this thing's negative. In other words, 4ac is greater than b squared, so it's going to turn out negative. Then you have two complex solutions with imaginary numbers in them. Sort of a big blue yes. But all three of those cases give us solutions for our differential equation. Okay? Now here's what they are. I'm unfortunately going to have to erase everything on the slide because I have no more room to work. Okay? So let's erase all that ink. Okay? Now, again, let's review what we would have there. Your M1 and M2, I didn't write it that way, but they did. Okay? One's with the plus and one's with the minus. Okay? The first one, M1 and M2, are real and distinct. Okay, what does that mean? That your discriminant, b squared minus 4ac, is greater than 0. Greater than 0, not greater than or equal to, greater than 0. You have two real solutions. Okay? Now, if that's the case, here's your general solution. Y is equal to C1 e to the M1 x plus C2 e to the M2x. That's it. Two real distinct solutions. That happens anytime your b squared minus 4ac is positive, greater than 0, then those are your solutions. Exactly what you would expect. Now, if that auxiliary equation could have been factored, then the M1 and M2 are rational numbers. If it wasn't factorable, then M1 and M2 are irrational numbers. But they're still fine. They're perfectly good solutions. Okay, there's the first case. Here's the second case. The M1 and M2 are the same. Real and equal. In other words, M1 is 7, M2 is 7. Okay? That's a repeated root. And that happens. Okay? When does that happen? That happens when b squared minus 4ac is equal to 0. In other words, these two solutions, M1 equal M2 equal minus b over 2a. If you have to know what it is, there's the answer based on your a's and b's up there. Okay? Now, we still need two solutions, but if you put y is equal to M1 C1 e to the M1x plus C2 e to the M2x, but M1 and M2 are the same, those are the same solutions. Those are not linearly independent. So that doesn't work here. Okay? Now, but what does work, when you have a repeated root, you can do your y1 would equal C1 e to, well, let's just leave off the C for now, e to the M1x. That's the only M you have, M1. But then based on what we just did in 4.2, your y2 would then be y1 times the integral of minus okay. See, my M1, remember, and M2 were both minus b over 2a. When you plug that around, what you wind up with, and they just throw it down here without all that much justification, but what you get is your y2 is equal to y1 minus y1 times the integral. I'm going to write it the way they do because they're leaving out so many steps. 2m1x over e to the 2m1x, okay, dx, which is just 1. So this would be y1 times x, okay? But your y1 was e to the mx times x. So I'm going to put the x in front. So there is your second solution. So your general solution then is y is equal to C1 e to the m1x, or mx. There's only one of them. So mx plus C2 x e to the mx. Okay? That's it. You can put the ones there if you want to, but that is your general solution when the two constants, when the discriminant is 0, the two constants are the same, minus b over 2a, that's then would be your m. Okay? You just put that extra x in between the C2 and the other one. Linearly independent, and they are definitely solutions. All right. Now, case 3. This they call case 1. This they call case 2. Case 3. Okay? What if your M1 and M2 are complex, which means, of course, that the b squared minus 4ac is less than 0. That's a negative number. So you're going to have an I there, okay? Now, what you wind up with then, this is a little awkward but true, your M1, the first one is going to be some alpha plus I beta. Your M2 is going to be alpha minus I beta. Now basically you wind up with two complex solutions, but they're complex conjugates of each other. One's with a plus, one's with a minus. Complex conjugates of each other. Okay. Now, if you were to write your solutions then, here's how it would look. Y is equal to C1. Now, this time they make it a capital C. Now, one reason for that, I think, is they are now allowing it to be a complex number. Not just any old constant, but even a complex. E to the, okay, your M1 is alpha plus I beta x plus C2 e to the alpha minus I beta x. Okay? Yeah. All right. Oh, what a mess. Right? But here to the rescue comes good old Euler. Remember him? Huh? Euler, right. Yeah. He was one of the most prolific mathematicians of all time. I mean, it's incredible. If you think about, back at a time before we had calculators, before we had computers, before we had typewriters, before we had any convenience, when everything was written by hand, pen and ink, probably parchment and quill, with dipping it into an inkwell. When we're way, way, way back there, he produced, it seems like to me, something like 200 or 300 papers in his lifetime. Major, major mathematical works. Okay? How in the world did he do it? I don't know. And some of these were breakthrough works. Things no one else had even conceived. And here's one of his. This is called Euler's formula. E to the I theta is equal to cosine theta plus I times the sine of theta. That is Euler's formula. Okay? Where theta is any real number, and they do have a asterisk by there, it can be obtained from the Maclaurin series, and then they give that and substitute it. X equal I theta, you go on from there, then separating the series into real and imaginary parts, the plausibility thus established, we can adopt that as a definition of E I theta, this thing right here. Now that doesn't look a whole lot better to me, okay? You have a real part and you have an imaginary part, so now you've introduced another another real number here, theta, and that's the argument of an exponential function raised to an imaginary power, and it's also the argument of a real argument of a cosine and a sine, but the sine is multiplied by imaginary. So that seems a little bizarre, but if you remember, you can do this as e to the alpha times e to the I beta, right? If you have same base, sum of exponents, you can write that as a product. E to the alpha times e to the I beta. And this would become e to the alpha times e to the minus I beta. So here you have your e to the I theta, or beta, okay? And so you could write this one that you had here, the one that was e to the I beta, as cosine beta plus I sine beta. This one would be cosine beta minus I sine beta. And when you add those together, eyes go away. You only have real pieces. No more imaginary pieces. Oh, thank you, Euler. You just got rid of our eyes for us. Okay? Now,
You can also get rid of eyes by like squaring it, right? Is an I squared equal to -1?
it is, but what's your justification for squaring?
I don't know
Yeah,
justification.
right. But this, for any value, this works. Okay? Now, this may seem bizarre, but let's just jump to the bottom line. I mean, if we went through all these steps, there are enough steps here to literally drive you crazy. Okay? So let's just jump to the bottom line, and here are our two solutions. Y is equal to your Y1, C1, e to the alpha x, where alpha is the real part here, okay, times cosine of beta x, okay, plus C2 e to the alpha x. That doesn't change, plus, no, I'm sorry, times sine to the beta x. So you could factor out the e to the alpha x from both terms, e to the alpha x times C1 cosine beta x plus C2 sine beta x. There is your solution anytime these m's come out to be complex conjugates of each other. You can just write them down this way, okay? Where these are the complex conjugates, just take the alpha, put it with the e to the alpha x, and then take the betas that you have here and put one with the cosine, it with the cosine, and it with the sine. Okay. So let's do example 1. Okay? All right to erase? Oh, wait, I'm sorry. I'm so sorry. What did you need?
Just the last part.
Last part. Okay. All right. So the last case, case 3, was when your b squared minus 4ac was less than 0. It was negative. That square root was negative. What you wind up with then is a situation that your m1 is equal to alpha plus beta plus I beta, and your M2 is equal alpha minus I beta. Okay, I think I've said that adequately. Yeah. Okay. Now, what you do with that, these are your, those are your two solutions. So what your general solution is, y is equal to e to the alpha x, there's your alpha part, the real part, put it with e to the alpha x, times c1, there's your arbitrary constant, cosine beta x plus c2 sine beta x. Is that what you needed?
Yes, sir.
Okay. Anything beyond, before that or beyond it or anything? Okay, there's your case 3 solution. It's a little more involved, but look at that. We got rid of the eyes completely. The eyes didn't have it anymore. Okay. All right. Now can I erase?
Yes, sir.
Okay. Now, we're going to do example 1. Here's a differential equation. 2y double prime minus 5y prime minus 3y is equal to 0. Okay? Now, just a reminder, linear, second order, ordinary differential equation with constant coefficients. There's a key. Constant coefficients. Okay? Now, obviously here, I think obviously here, second order, you can't really do separation of variables. Okay? But this with constant coefficients, goes straight to your auxiliary equation. What would that be? 2m squared minus 5m minus 3 equals 0. Now where did that come from? Here's your assumed solution. Y is equal to e to the mx. There's your assumed solution. You get this out of it. Okay? Well, this will be a solution. Y e. So guess what you're going to try first? Want to try factoring? Or you want to go straight to the quadratic formula?
Let's go, it's going to be m minus 6.
Ooh, look at that. Okay. Here's how I do it. Now, you may be doing the same thing, but let's do this. The only possible factors, see, I unfoil it. You know, you foil by multiplying, unfoil it by factoring, okay? Only possibility would be 2m times m, right? That's the only way you're going to get 2m squared, right? Look at the sign of the last term. That's a minus. Now, we don't know what, but you know they got to be different signs. So let's just do, what, plus minus? And the only possible factorization for 3 would be 1 and 3. So you want to try it? 1 and 3. Okay. That's probably not right, but let's see. Foil it and see what you get. 2m squared, that's when you do this one. And then the outer gives you minus 6m. The inner gives you plus m. Oh my goodness, did I luck out? And the last gives you minus 3. And that gives you 2m squared minus 5m minus 3. That I can't believe I just lucked into that. Okay? But there it is. It does factor. Right? Now, if I had put the plus and minus signs in the wrong places, it wouldn't have factored right. Put the 1 and the 3 in the wrong places, it wouldn't have factored right. But you just do trial and error until you get them right. I just lucked out and got them right the first time. So there's your factors. So what does this tell you? Either 2m plus 1 is equal to 0, or m minus 3 is equal to 0. What does this tell you about m?
M equals 1/2.
Negative 1/2. Or
M equals 3.
Equal 3. Okay? One or the other. So here's what your solution is. Y is equal to C1 e to the minus 1/2 x plus C2 e to the 3x. There's your answer. Right there. It factored, whatever those factors are, the values of, that make it equal 0, those are your m's there. And those are linearly independent solutions. There's your general solution right there. Okay? Now, they wrote it as C1 e to the minus x over 2. I put negative 1/2 x, that's fine, plus C2 e to the 3x. Okay. Good deal. Wasn't that fun? That's it. There's your solution. We just solved our first higher order differential equations all by ourselves. They didn't give us a solution. We came up with both of them ourselves. They're linearly independent. It's a second order equation, differential equation. You need two constant arbitrary coefficients. We got them. That's your general solution.
So I do have a question.
Okay.
If we're doing basically just, we're looking at a problem and we're kind of foiling it, doing quadratics. Some of them are going to be a little bit too messy where we can't foil it, so we will have to go to the...
You'll have to use quadratic formula.
Quadratic?
Absolutely, yeah. The next one you're going to be able to foil too. Or you may not even need to foil it. Let's do it. Can I erase this one?
Yes.
Yay or nay? Okay.
Yes.
How about this one? Y double prime minus 10y prime plus 25y is equal to 0. Okay? Now our assumption here is a linear, second order, ordinary differential equation, constant coefficients, so our assumption is y is equal to e to the mx. With that being our assumption, what would be our auxiliary equation?
Well, yeah, I think it's something that equals 25 or something that multiplies to 25.
Okay, but give me the equation first.
Oh, m squared.
M squared?
14m?
No, that's a 10.
Oh, that's a 10.
Making fun of my writing, I see.
Oh.
Okay. Minus 10m
Plus 25.
plus 25
So you're
equal
0.
0.
M minus 5 times m minus 5.
Equals 0. So what are our solutions?
5.
M equals 5. Only one solution. But it's a second order differential equation. You need two independent solutions. And you can't say C1 e to the 5x plus C2 e to the 5x. Those are not linearly independent. They're the same.
So
Yeah.
would the answer be y e to the 5x?
Okay, that's one solution. Y is equal to C1 e to the 5x. But you need two linearly independent solutions. What's the other one?
Plus C2 e to the 5x.
If you did that, they're not linearly independent. You could add those two together and get C3 e to the 5x. That's still just one solution. What was our case 2 before? Here's what it is. Plus C2x e to the 5x. From that reduction that we did in 4.2, put that other function, that x in there. And that's all you need, it's just the x. Okay? Now those are linearly independent. Two arbitrary coefficients, you got it. That's it. Okay? C1 e to the 5x plus C2x e to the 5x. All right. I want to try the C1. Y double prime plus 4y prime plus 7y is equal to 0. That's a linear, second order, ordinary differential equation with constant coefficients. What's going to be our assumption?
M squared plus 4m plus 7.
Okay, it's going to be y is equal to e to the mx. Okay, and just like you said, that would be m squared
Plus 4m.
plus 4m
Plus 7.
plus 7 equals 0. Okay? Yes, you're going to have to. How does that go? M is equal to minus 4 plus or minus the square root of 16 minus 28. Oh, isn't that pretty? Over 2. Okay. Oh, yuck. This is minus 4 plus or minus the square root of, what's 16 minus 28? Negative 12 over 2, which would be minus 4 plus or minus,
That'd be 12i.
second,
Wouldn't that be 12i?
root 12i.
Root 12i.
Okay, but the root 12 we could do something with.
We could, it'd be 2 root 3.
Ah, got it. Plus or minus 2i times root 3 over 2. Now the good news there is the 2 can go into 4 twice and 2 once. So this would be now be minus 2 plus or minus I root 3. Okay. What's that?
I was looking at the. I got it.
Okay. Now, this is a good old case 3. Complex conjugates. That's what you get from your auxiliary equation. Okay? Now, what was our solution? Charles had me write it again. Remember how that went? Y is equal to?
C squared.
Is e to the
minus
minus 2 x, right? That was, I was trying to remember what our variable is, x, times, that's the a part, e to the alpha x, right? Times C1 cosine beta. What's your beta here?
Sir,
Say again?
beta.
What is your beta?
Beta is going to be
Square root of 3. The square root of 3 times x plus C2 times what usually goes along with cosines?
Sine.
Sine of,
beta.
which is square root of 3 x. There it is. The alpha goes here in front, and then the beta goes as the argument of times your variable, both times the variable, of your cosine root 3x, sine root 3x, arbitrary coefficients. Plus in between, don't put a minus. It doesn't matter. The C could absorb the minus sign, but that's what you get. Let's see how they did it. E to the minus 2x, there's your alpha, times C1 cosine root 3x, plus C2 sine root 3x. Now, I just want to issue a warning. When you're doing this, be sure that you identify that the root stops here, okay? I like to bring a little house down here just to indicate that x is outside the radical, not inside the radical. In fact, quite often I like to write it cosine x root 3. The book doesn't like that, but I like to do it that way. Okay? Does that make sense?
So is the alpha going to be
The real part.
It's your B, right?
It's the real part. The minus 2.
And then
The beta is going to be the real part of the imaginary part, you know, the coefficient of the I, whatever that is. You don't need plus or minus sign, just keep the sign with the alpha, the beta is just that number. Whatever it happens to be.
Is this a case 3?
What's that?
Is this case 3?
Case 3, exactly. When you have the m less than, the discriminant less than 0. If that was a negative 12, you're going to have to go to case 3 here. But the good news is the minus sign comes out as the I, and then 4 comes out as a 2, and it leaves you root 3. And then 2 gets canceled out, divided out because of the 2 in the front. That's what happened to that. It was originally a minus 4, but it got reduced to a minus 2. Okay? Now, ready for example 2, or do you want to take a little break before we go to example 2?
I'm good with the break.
What's that?
I'm good with the little break.
Yeah, I think I am too.
You gotta go to the bathroom?
Yeah, I need to go. Yeah. I mean, I can go without. All right. Don't need example 1 anymore?
No, sir.
Let's go to example 2. An initial value problem. here is your differential equation for y double prime plus 4y prime plus 17y is equal to 0. With the initial condition, y of 0 is equal to negative 1, and y prime of 0 is equal to 2. Now, it's been a while since we did an initial value problem. Here's the key to an initial value problem. A key, one of the keys. Number one, it's a second order differential equation. You've got to have two initial conditions. Whatever your order is of your differential equation, you've got to have that many initial conditions. Now, why initial condition? Well, this time, the value for x, or whatever your independent variable here, is 0, which makes sort of sense as initial, but it doesn't have to be 0. What it does have to be, the same x here has to be there. If you're doing y of 0, you have to do y prime of 0. If you do y of 15, you have to be y prime of 15, okay? You have to use the same value. That's what makes it an initial value problem. These are just the values for the y and the y prime, but the x's, or whatever your independent variable is, has to be the same for an initial value problem. Okay, where would you start? Anybody?
4m squared plus 4m plus 6.
Okay, he likes to go straight to the auxiliary equation, which is a good thing to do. 4m squared plus 4m, what was the rest of it?
Plus 17.
Plus 17. What's the rest of it?
Equals 0.
Equals 0. Okay. Now this is all coming from, just remind yourself, this is all coming from the assumption that y is equal to e to the mx. That's where the m came from. Okay? Now, what would you do next?
I would try to factor it.
Yeah. Think you can?
What's, think of 4 times 17, 28, 68. I don't know anything equals 68, so we're going to do quadratic formula.
Yep. How does that go?
Negative 4.
M is equal to negative 4.
Negative 4 plus or minus.
Plus or minus.
Square root of 16 minus. Give me a calculator out, actually.
16 times 17.
16 plus 272.
272?
Yes, sir.
Okay, all over?
8.
8. Okay. Any first impressions here?
Yuck.
What?
Yuck.
Yes, exactly. All right. Let's see if we can clean up the yuck a little bit, but it's still going to be yuck. Minus 4 plus or minus the square root of, what does that turn out being?
Negative 256.
Negative 2 what?
56.
56?
256.
66. Okay.
66.
Over 8.
No, it's 16 minus 272. That's 256.
256, right? Yeah, that's what I said. I thought you corrected me and said 266.
No, sir, I said 56.
Okay, 256. Okay. Now, what do you think we can possibly do here?
We could make that a negative 1 plus or minus.
So maybe make that an I here?
Yes, sir.
Okay.
Well, I was gonna say, like, could we make that negative 4 and that 8? Could we reduce that to negative 1 over 2?
Yes, we can. But let's go on and do this one too.
Yes, sir.
How about the 256? What
That's
can it
16.
become? Huh?
16 times 16 equals 2.
16 times 16? Is that what you said? Yes, it is. So that would be 16i, right. So I've got it backwards there, but it's okay. 8, and this would be minus 1/2, there's the real part, plus or minus 2i. There's the imaginary part. Agreed? Okay with that? Okay. Now, what do we do with that?
Well, I guess we add it. I'd say we add it.
What do you mean add it?
Well, not really. You can't add it. I was just kidding. We're gonna have to do that We're gonna have to do that like beta and cosine thing.
Oh, yeah, that thing.
So
How does that go?
alpha's gonna be
Y is equal to,
y is equal to e to the negative 1/2 x.
got it, times,
Times cosine
okay, what a C1?
c1
Cosine,
cosine 2i
not I, 2x.
2x.
Whatever your independent variable is.
Yes, sir.
Next,
Plus c2 sine 2x.
2x. Okay. Now, there's your general solution with your arbitrary coefficients in it. But we have an initial condition, so let's plug that in. When x is equal to 0, what is your y? Y is equal to, what's e to the 0?
E to the 0 is just 1.
1, okay. Then you'd have a C1. What's cosine of 0?
1.
1, okay. Plus, what's the sine of 0?
0.
0. So obviously, oh, okay. So that'd be 0. So this is equal to negative 1. So C1 must be a negative 1.
Are we saying it's negative 1 because y is equal to negative 1?
Wait just a second. I was trying to clean that up. Okay, say that one more time.
And we're saying it's equal to negative 1 because the initial condition says y of 0 is equal to negative 1.
Yeah, when x is 0, y is negative 1, and this just turned out to C1 here. Well, that turned out a 1, that turned out a 1, and that turned out a 0, so C1 is equal to negative 1. So we got the first part of it. What do we do next?
We would plug in negative 1 for C1 to solve for C1.
Okay, we could do that. So this is equal to e to the minus 1/2 x times minus 1 cosine 2x plus C2 sine 2x. Is that what you were suggesting? Okay. Now what do we do with that?
Would we plug in the initial condition again?
Okay, and what's your second condition?
Yeah, I don't know, actually.
What does it say?
Y prime.
Ah,
Take the derivative.
you got to take a derivative. All right, so let's do that one. Okay, that's your y here. So y prime, and unfortunately this is going to be a kind of a multiple product rule type thing, isn't it?
Yeah.
Okay, so what are we going to have? And rather than having a minus 1 there, let's just make that a minus cosine. A little bit neater looking. Okay, so what do we have now?
Well, we're going to do like multiple. Yep, so we're going to do the derivative, let's do the chain rule, technically. So negative 1/2 e to the x
E to the minus 1/2 x Right.
times that
minus cosine 2x plus C2 sine 2x. That's what you meant?
Yes, sir.
Okay.
And now plus
Plus
e to the negative 1/2 2 sine 2x
Okay.
plus 2c2. Wait, is that product rule on that one too?
Say that one more time.
Would that be product rule on that c2?
No, C2 is a constant.
Okay, cool. 2c2 sine 2x, or cosine 2x.
Cosine 2x. Okay. Now we've got y prime. Let's plug in. That's y prime at any value x. Let's plug in y prime at 0. And what would that be?
Negative, well, let's just say this is going to be negative 1/2.
Second?
Negative 1/2.
Negative 1/2.
Because e to the 0
Right.
is 1.
Right?
Just give me 1 second. Minus 1 plus 0
Okay.
plus 1
Okay.
0
Okay.
plus 2c2.
2C2. All right. So if I'm not mistaken, oh, and that's equal to 2.
So yeah, we just put 2 equals. So yeah,
Okay.
that's equal to.
All right. So now we've got 1/2
Plus 2c2 equals.
plus 2C2 is equal to 2. Let's multiply everything by 2. You get 1 plus 4C2 is equal to 4.
Get rid of that 1.
Right?
So c2 is going to equal 3 over 4.
Yeah, 4C2 is equal to 3, and C2 is equal to 3 over 4. Perfect. Okay? So now our solution is, or to write it here, y is equal to e to the minus 1/2 x times minus cosine 2x plus 3/4 sine 2x. That should be it. Okay? Let's see what they got. If I can read this. Y is equal to e to the minus, they put x over 2, we did 1/2 x, is fine, times of minus cosine 2x plus 3/4 sine 2x. Done. Okay. Now, just a little bit of a visual here. Here's the function. Of course, when x's are negative, which they can be because this is good for all real number x's, this thing blows up, right? Gets bigger and bigger and bigger because minus times a minus gives you positive, each a positive number. It's going to be pretty big. So it's getting quite big on the negative side. But on the positive side, this is going to 0. These stay between plus or minus 1, but this is going to 0, so we have one of those damping functions. And these are blowing up out here, but damping over here. So that sure enough looks like this is your, in time, it's just going to get closer and closer to 0 because this is going to dominate the e to the minus 1/2 x. Okay. On the negative side, it blows up like crazy. All right. Now, they have a little I found an interesting kind of subtopic here. It sort of sounds like it's who you know, and this is that. Oh, I should have asked anyone needed it anymore. I hope not. Okay. 2 equations worth knowing. Okay. Here's one: y double prime plus k squared y is equal to 0. Okay. The other one is y double prime minus k squared y is equal to 0. Now, K is always real, not complex or imaginary, okay? So, what does that first one, how does that speak to you? Second?
K is equal to M.
Second?
K is equal to M.
Okay. Or, okay, let's see how you got that. You got M squared plus K squared is equal to 0. So, wouldn't that be K squared is equal to
Negative.
negative M squared, which means, yeah, that means the,
Oh, but on the
And-
second one you can.
yeah, the second one is much better, okay? But the first one, the M must be complex, because they told you K is real, not complex. So the M must
So
be.
why can't we just put M squared plus K squared equals 0 and then take the square root of both sides?
Okay, we'll try that. Okay, you're saying M squared plus K squared is equal to 0, and then,
Square root of both sides.
okay, and what do you mean by that?
Well, I mean, if square root of 0 is 0.
Right, I can do that side, you're right, okay.
Square root of M squared plus K squared is going to be M plus K? Or no?
Oh, wait, new math, I didn't know that one. Oh. Yeah. Because guess what? If M is anything other than 0, and K is anything other than 0, ain't no way, right? Because M squared is always positive, and K squared would always be positive. Unless, of course, M was complex. And then you can do it. Because they told us up front that where K is real, okay? So that means M is equal to IK. Would you agree? In fact, I would go so far as plus or minus IK.
Yes.
Yes. Okay. Now, if that's the case, what is your solution? Y is equal to E. Okay, what's E?
E.
Okay, but
E to,
just write E down? Okay.
E to the IK
No, that's not how it goes, does it?
plus or minus IK?
Okay, that's not how it goes, does it?
MX?
Okay. Is it multiple choice for me, or what? Okay.
Give
Oh,
me
yes,
some
you do.
multiple choices.
Huh?
Give me A, B, or C, or D.
No. What's your real part of this?
M equals K.
No.
I.
K is the imaginary part. The real part is 0. It's 0 plus or minus IK, right?
Yes.
So e to the 0x, which is just 1. So, all right. So, there's no e there. It's a 1. Okay. All right. And what's the rest of it be?
I gotta think about it.
I figured that.
I hit a brick wall.
Okay.
Do we C squared?
Huh?
C squared.
C squared.
E squared?
C.
E.
C.
C squared. Okay. C is a constant, so it's whether let's call it C sub 1. What follows? What
Minus K. Plus K. K.
Plus minus K squared.
say again?
Plus minus K squared.
Okay. All right. This was case 3, remember?
Oh.
Oh!
Hey, no point of yelling.
Huh?
There's no point of yelling now.
I can't hear you.
No, you're fine. C1's parentheses.
You don't have to have a parentheses.
Sorry.
Cosine.
cosine
X.
kx. That's your beta. The k is your beta here. It's the thing that goes with the I, okay? Plus
C2.
C2
Sine.
sine
K.
k
X.
x. Okay, all right. Now,
Shouldn't it be minus K though? Since it's plus or minus?
no. Remember, that's always the beta part is just sine and cosine. Yeah. So don't put a plus or a minus in there. If you did, all it does, if this was a minus here, that's the same as cosine kx. If this was a minus here, that's just minus sine of kx. Well, then you could incorporate the minus sign in C2. Okay. But let's pause just a moment here, right? What is the derivative, first derivative of cosine? Well, let's just do the first derivative of this one. What would that give you?
Minus sine.
Okay, that would be minus C1 k sine kx, right? This one?
C2 or K C2 cosine K.
Plus, right? Now take the second derivative.
Negative cosine or negative K squared cosine KX plus
And this would be?
minus K squared C2 sine KX.
And isn't that, then when you add those together, you get exactly 0.
I guess so.
Yeah, because when you take the first and second derivative of sine and cosine, all they do is change signs. And that makes that true. So sure enough, that's just hopefully what we'd expect it to be. All right, how about this one over here? What would that give you?
Oh, you're asking me a question.
Yeah.
Y or M squared minus K squared equals 0.
Which would result in
M equals K.
That's one possibility.
What? M equals plus or minus K?
Yes, m is equal to plus or minus k. Exactly. I was going to factor it for you, but you saw it without me factoring. Okay? And so therefore, what would your solution be?
Y equals, there's no imaginary numbers.
No.
There's no beta.
No. Where did this thing come from? This one too, by the way. What was your assumption? Y is equal to?
E to the MX.
M to the mx. Okay, and what's your m's here?
M. E. Okay.
Y is equal to C1.
E to the M equals plus or minus K.
Yeah, so which one you want to go with first?
Plus K.
Okay, kx plus
C2.
C2.
E to the negative K.
Got it. Linearly independent solutions. That's it. And sure enough, you can take as many derivatives as you want to there. The signs are going to stay the same, SIGN signs, and you're just going to have k's in front, and that sure enough is what you got. K for the first derivative, k squared for the second derivative. And so you get that. Okay? Now, they also do this one in a different form, and I don't really care for it, but they do suggest it, so I'll just show it to you. That's the same as C1 hyperbolic cosine of kx plus C2 hyperbolic sine of kx. I don't really care for the hyperbolics that much. I just assume keep it in the exponentials. Okay, that's just my preference there. If you find that your major uses hyperbolics a lot, don't ignore them. Use them. What's that?
I hope my major knows.
Me too. All right. Well, what if you have higher order equations? Okay? All right for me to erase?
Yes, sir.
Okay. In general, to solve an nth order differential equation where all your coefficients are constants, real constants, we must solve the nth order polynomial equation. Your auxiliary equation would then be a sub n, m to the nth, okay, plus a sub n minus 1, m to the n minus 1, plus a sub n minus 2, m to the n, I can't write, minus 2, plus dot, 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 all the way down to a sub 3, m cubed, plus a sub 2, m squared, plus a sub 1, m, plus a sub 0 equals 0. If it's a linear homogeneous solution. Okay? Now, if all the roots are real and distinct, now that's a big assumption. If they're all real and distinct, then your general solution would be, for each one of these, you have a separate solution. M sub 1, M sub 2, M sub 3, M sub 4, and so on. So your general solution would be C1 e to the m1x plus c2 e to the m2x plus c3 e to the m3x plus dot, 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 all the way down to and including c sub 3, c sub n minus 2 e to the m minus 2 x. That's not how m sub n minus 2. That's how it should be. Okay, I'm getting a little lost here. No, they go to k's now. Okay. No, they leave it as n's. Okay. I was going to put a few more in there. Plus c sub n minus 1 e to the m sub n minus 1 x plus c sub n e to the m sub n x. Okay. So in other words, a linear combination of those solutions. That's if they're all real and distinct. Okay? Now, case 2, that would be case 1. Okay? Just like we would expect. Okay? But case 2, remember if you have n possibilities here. What if you have some of those as duplicate roots? Okay? Then for every duplicate root, you have to do an x times e to that root. Okay? And if you had triplicate roots, you'd have x and an x squared. If you have 4, multiplicity of 4, you have x squared, and an x cubed. Okay. Now, the complex, if you had complex roots, remember if those are real coefficients and they all are constants, then the worst you can have is complex conjugates. Okay? So for every complex conjugate, you have e to the alpha x times a cosine, constant times cosine beta x plus sine beta x. Okay. So you have a lot more possibilities there. Okay. Should also be remembered when the coefficients are real, complex roots of our auxiliary equation always appear in conjugate pairs. So if you have a cubic polynomial equation, you can't have more than 2 complex roots. Got to have at least one real root, and then the others 2 can be complex. So let's do example 3, which is a third order differential equation. Okay, here's what we got. Y triple prime plus 3y double prime minus 4y is equal to 0. Where would you begin?
M cubed.
Okay, you go straight for the auxiliary equation, which is good. Okay, m cubed
Plus 3m squared.
3m squared minus 4 equals 0. Now, where do you go from there?
We take a derivative.
Let's not, okay? Simpler than that. Okay? One thing that makes it simpler is look at your coefficients. Okay? Now, the easiest m to assume, and that's all we're going to do is assume, is m is equal to 1. What would you have if m is equal to 1?
1 plus 3 minus 4, which is 0.
And is it? So m equal 1 is a solution. Okay? Just by observation, you can see that m equal 1 is a solution. Now, y'all remember your good old synthetic division? Oh, no, you don't, do you? Oh, man, it's easy, though.
I think I remember it. It's
Pre-cal.
It's what? Free cal, exactly. You mean we have to remember that stuff? Why you reckon you took it? Okay, here's what you do. You put that solution, 1, outside the box. Inside the box, you put the coefficients of your quadratic, not quadratic, your polynomial equation, which would be what? 1, 3.
Minus 4. 0.
0 minus 4. You have to account for every term. Here's another little key that I always use. Count the number of terms you have there. It's got to be one more than your maximum degree. That's a 3. You got to have 4 terms. You have to put a 0 in for the missing linear term. Okay? Now, next thing, skip a line, draw a line. I've never seen a book tell you that, but I drew it. Okay? Bring down the 1, and then from here on you multiply and add, multiply and add, multiply and add. So multiply 1 times 1, you get 1. You add, you get 4. You multiply, you get 4. Add, you get, you're stuck on 4s, aren't you? Multiply, you get 4, and add, you get 0, which you knew you better get because that's your remainder, and that you knew 1 would go into it. So what does this represent? That quotient line at the bottom. This, yeah, that's not x, but m squared
Plus 4m.
4m plus 4, and set that equals 0, and either factor a quadratic formula.
Oh, you can do, it's going to be m plus 2 times m plus 2.
You got it, okay? Which is m plus 2 squared, blah, 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 okay.
M equals negative 2.
What's that?
M equals negative 2.
M is equal to negative 2. Okay, perfect. And it's a double root, right? All right, now let's go back. Where did this thing come from anyway?
Assuming m equals 1.
Okay, yeah, but where did even this come from?
The original problem.
Okay, but why does that show up? What's your assumption?
y equals e to the mx.
That's it. Okay, here you got an m, there you got another m, but that's a repeated m. So remember how we do?
Y equals
to C1.
Y is equal to C1.
E to the 1x.
X, okay. Plus
C2.
C2. E to the what?
Negative
Negative 2x plus C3. You have to have 3 because it's the third order. But with the repeated root, what do we put there? Go back to case 2.
I don't see. C3x e to the negative 2x.
You got it. There you have it. 3 linearly independent functions, 3 arbitrary coefficients. There's your general solution. Got it? Good deal. Let's see how the book did. Y is equal to C1 e to the x plus C2 e to the minus 2x plus C3x e to the minus 2x. Perfect. Okay. You think we have time for example 4?
Is it just doing this stuff?
What's that?
Is it just like this stuff? Is it just like this stuff?
It's similar.
Okay, let's do it.
Let's do it. Okay. Y'all need this a little bit longer?
I'm good.
Okay. I remembered to ask that time. Sorry. Okay. All right. Example 4. They write it a little differently, but let's see. D4y dx to the fourth plus 2 d2y dx squared plus y equals 0.
So that would be y to the fourth, y4 prime, whatever,
Yeah.
yiv.
That's how some do it. Some put it, the number 4, I'm used to the old IV, okay?
Plus 2y double prime plus y. And then you rewrite that as m to the fourth plus 2m squared plus 1
Yep,
equals 0.
okay.
I guess you want to solve that.
Yes, of course.
I'm stuck.
Okay, not really, but let's do it. Let's try factoring it first, okay?
Oh, wait, never mind.
Oh, yeah, okay.
M squared.
You got unstuck in a hurry, didn't you? M squared
plus
and
1.
M squared
Yeah, plus 1.
plus 1 and a plus 1.
Yeah, I'm not stuck.
Goodness gracious. Okay,
So then, m squared equals negative 1. What? M squared equals 9.
okay, you got M squared equal negative 1, is that what you said? Okay, I'll buy that.
You do the square root.
Uh-huh.
M equals I. And if you write it as I squared, since it's no.
That would work. And this also gives you M squared equal minus 1. So M, again, is plus or minus I. So you got 2 there's your 4th degree differential equation. So you got 4 roots, but both of them are repeated. So this is kind of a combination of
Case 2.
case 2 and case 3. You wanted to do it, right?
Yes,
Okay. Get me started.
Y.
Got it. Very good.
C1.
C1. Good. Second step.
E to the IX. Wait, E to the KX. No, E to the...
Multiple choice again, huh?
E to the... Is it not E?
Okay, what's your real part?
No real part.
That means it's a
0.
0. And e to the 0 is?
1.
Okay, so let's not do that. Let's just leave it 1.
Plus C2.
Okay. No. The e to the real part would be on the outside of the c's anyway.
Mm-hmm.
And when you went straight to the c's, I thought you were forgetting about the e's. Okay? The c's, when you have case 3, what do those go with? Yes, you do.
Oh, God, I do know. Oh, it's cosine.
Cosine
X.
x
Plus C2 sine X.
sine x. Okay? Now that would be if they were just single ones, but it's a double one, so guess what we're going to have next?
C3.
C3, good choice.
Minus. No, cosine.
Now go back to case 2. These are doubles.
E.
Not yet. No, we didn't have E in case 3. Case 2, we just did one with case 2 a little bit ago. Yes, you did.
C3 X E.
Oh!
Oh, okay. Double back.
Yeah. Plus
C4.
C4.
Sine X. X sine X.
X sine x. Okay. You knew it. Okay. Let's see how they did. C1 cosine x plus C2 sine x plus C3 x cosine x plus C4 x sine x. That's it.
Would this be a final question?
What's that?
Would that be on the final?
It could easily be on the final, right? Aren't they fun? Yes.
I mean, I'm cool if you make like all we did today in the final.
What's that?
I'm cool if you made all we did today in the final. Yeah, up to this day.
It will be on the final. We'll do a little more too. Okay. All right. So we're going to need to I guess we ought to next time go over a little bit on the top of page 139. So we'll do that. But made great progress today in spite of all the hesitations. Homework exercises. Oh, we almost finished 4-3. You can do any of the odds 1 through 13 that are in the back of the book, any of the odds 15 to 27 that are in the back of the book. Think you could do any of the odds 29 to 35 that are in the back of the book. Let's hang off there and we'll pick up the rest of those next time. Okay? Good deal. All right. That was fun, wasn't it?
Sure.
Sure.
Oh,
Okay.
day's work right there.
Yeah. All right. And we'll see you on Thursday and then Tuesday, and then I'll give the final either Thursday or Tuesday, but we'll have class both days.
So it's going to be, the final could be this upcoming Thursday, Tuesday?
Yeah, I'll either give it to you Thursday if I have time to run it off. I'll either do that on Thursday, or I'll give it to you for sure the following Tuesday. But I'm almost certain I can get it run off in time for the Thursday. I mean. Okay. All right, good deal. Take care.